Hello and welcome to today's webinar on the topic of tan delta testing on rotative machines. My name is Andrei Shepcic. I'm an electrical engineer working for Altanova. I function as a regional area manager and I have some experience in this topic, and today I'm going to tell you a story how I learned about this and what it means for me to do this type of test. With me is also engineer Mariela Gastaldelli. She will be the person answering your questions in the questions section. So throughout the whole webinar, you are enticed to ask a question if there is something you don't understand, and Mariela from the other side, who sends her greetings, will be doing her best to answer your questions. Now at the end of the webinar, we might read some of them, and if there are some questions which are not answered, then we might answer them out loud. So I hope that today's topic will not take more than 1 hour of your time. I honestly started this whole presentation with the idea to make it only a half an hour webinar, but as the presentation grew, I realized that probably 45 minutes to 1 hour will be enough for today's session. So without any further ado, let us start with the topic in question. Rotary machines or generators and motors are essential in power generation and many industrial applications. So we need to be sure that they are in good health, that their electrical insulation is in good health. This is what we will be talking about today. So we will be talking about electrical insulation, and we will, when talking about electrical insulation, express that notion in measurable parameters like capacitance and tan delta. So capacitance and tan delta will function, you will see why, in the future as two parameters which are measurable, which tell us how good is our insulating system. So we will be able to determine, well, we won't be able to say exactly what is the age, but how old is our insulation, what is the water content, or should I say how much humidity is there inside, if there are some other impurities, if there is some thermal deterioration going on, and if there are any corona discharges and air pockets in our insulation. This is what these tests will help us understand if we have and how much we have them. Now, tan delta, or power factor or dissipation factor, is a comparative test, which means that also we will be comparing our present results with our previous results. That's why if some of you are not doing this test, I urge you to start doing it, because sometimes that is the best way how to evaluate the result. Also, in the tan delta measurement on rotary machines, we will be doing something which we will call tip up and a tip down test. We will see later what it is. So this is also something which is quite specific to rotary machines. Now let us take a step back also and clearly state that this is an offline and that this is an AC test. When we say an offline test, it means that you take your asset, your rotating machine, and you take it offline. You don't measure while it's being used. So in that aspect, it's an offline test. And it's an AC test. It's not a DC test. Why is it an AC test? Because of many reasons, one of them being repeatability, the other one being able to get more realistic environment similar to the working context, working procedure of that generator or motor. So if you do an AC test and the generator is usually generating AC current and voltage, then it's obviously better to do it with an AC current or voltage. Also, in the end, you will be able to check, as we said, the age of the insulation, contamination, and also the possibility of having some mechanical deformations. So why and how mechanical deformations? Well, let us now take one more step back to explain why is capacitance used to measure the insulating properties of our insulation. In order to explain this, we will say that the test which we will be doing is always done between two different voltages. So if we can have 0 and 10 kilovolts, we can have 0 and 5 kilovolts. But if we have tests done between two different voltages, then two different voltages mean that we are probably dealing with something which we saw before as a capacitor. So actually what we are doing is we are modeling the insulation of electrical insulation of a rotating machine as a capacitor. And this is confirmed by the IEEE definition that an insulation is a suitable non-conductive material or combination of materials which provide electrical insulation between two parts at different potential levels. So we have two different voltages, each on one side, and we have a dielectric in the middle. So that is basically the definition of a capacitor. This is the definition of a capacitor because we have two voltage levels, and in between we either have air or we have some solid type of insulation in the form of a band, or we have some kind of resin. So all types of insulation, which would be then this in the middle, this would be the insulation, and this would be, for example, phase A, and this would be the phase B, or this would be phase C, and this would be ground, as the story says. So it could be two different phases, or it can be a phase and ground. That's why we model the insulation as a capacitor, because whether we want it or not, the insulation always acts and has properties of a capacitor. Looking into the characteristics of the capacitor, you will remember that the formula for the most simplest capacitor is C equals epsilon A divided with D. Now, epsilon, having said that, is a multiplication of epsilon 0 and epsilon R. And epsilon R is what actually defines properties, insulating properties of a certain material. So if this epsilon R changes in due course of time, what is happening is that probably your material, your insulating material, is somehow getting some moisture inside of itself, or it might be getting some kind of air bubbles, or maybe it's overheating. And this is what we will be able to see during a tan delta test. So once again, capacitance equals epsilon times A divided with D. So if we measure this today and we measure again in 2 years and this number changes, what can change? This parameter or this parameter or this or some combination of these parameters. If epsilon changed, then the insulating properties of the material changed. As we said, water molecules, stuff like that. If A and D or one of these parameters change, then also the mechanical properties, the geometrical properties of this rotative machine have changed. So in that aspect, if the C changes a lot, then it could mean that we have a compromised insulation as well as mechanical defect. So, but with this, slowly, I hope you're starting to appreciate why are we actually measuring capacitance in order to reflect the state of electrical insulation. This is electrical value, this is mechanical value. Now, since we're talking about the capacitor, let's model this capacitor in our ideal world. In our ideal world, if we have an AC source and a capacitor connected directly to it, we will have the current running exactly 90 degrees in respect to the voltage. So voltage is lagging, current is 90 degrees in respect to voltage, exactly 90 degrees. But you see, this is an ideal, and of course, there is no such thing as an ideal capacitor. We will see as we proceed that tan delta is actually quantifying the difference between ideal and real capacitor. So the real one is the one we are seeing in front of ourselves. It is the insulation, and this real capacitor has another resistor connected in parallel to our capacitor. Now, this is more realistic way how you can portray, how you can present an equivalent scheme of an insulation in your rotary machine. Why is it made like this? Well, because there is always some finite resistance which will let some electrons pass through this. And even though it's a huge number of ohms, it's not infinite. And the thing is that the current passing through is generating heat. And this is the problem which many devices suffer from. We want to remove this heat or we want to control this heat. So long story short, with a real capacitor, we have some current which is in phase. That's important to say, with the voltage. And since it's in phase, it's creating issues. So this is ideal and this is realistic. If you draw everything in your excuse me, in the plane, you will see that here IR is 0, here IR is not 0, and the total current is not here. The total current is here. And then we have some angles here. Due to these angles, because we have some angles here, this is actually what we are measuring when we are measuring tan delta. But I'm getting ahead of myself. Let's just mention once again that the problem here is the heat. The problem here is the fact that since it's in phase, you see, with the voltage, it is creating a potential vicious cycle, a chain reaction that can lead to dramatic failures in our rotary machines. So in order to keep generators running smoothly, we need to know the state of our electrical insulation. So once again, let us repeat and let us define what we learned until now and define exactly what is a tan delta. A tan delta is the ratio of in phase or resistive current to the 90-degree capacitive current, or tan delta is IR over IC. If we draw this in the plane, we will see that this is the voltage, this is the capacitive current, and this is the resistive current. In reality, this current is very small. It's maybe like this long, and in reality, this line here is basically something like this, very close to IC, and this is actually the angle we are measuring. So tangents of this angle is IR over IC. If we play a little bit with the formula, we can also see that the tan delta equals 1 divided with omega RC, where omega is 2 pi f, which is a fixed value. So we can see that basically we are determining the R and the C, the R and the C of our equivalent scheme. And for nomenclature purposes, I just want to say that tan delta has another name. It's called a dissipation factor. Sometimes these names differ from one country to another. In some countries, we're not using the name tan delta, we're using the name power factor, especially in US and some other countries. Power factor and tan delta are essentially very, very similar. They're very similar because you see the tan delta is defined like IR over IC, and the power factor is like IR over I total. You see this vector here? So if you can imagine this vector being very close to IC, whether you divide IR with IC or IL, which is very similar to IC, you would get a very similar result. Long story short, for the angles of delta being up to 10 degrees, the value of IR and the value of power factor and tan delta are almost the same, as you can see here. So there are, of course, formulas which can recalculate tan delta from power factor and power factor from tan delta. But in general, you will see that what we are trying to say here, power factor or tan delta, will more or less give you the same result, more or less. Now, I will later mention why they will not give you the same result, because there is one specific thing regarding rotative machines in respect to some other devices which can be tested for tan delta. Now, let us stop here for a second and just make a small recap. Tan delta is a test which can be done on many, many different types of primary equipment. You can do that on a rotary machine, but also on a power transformer. You can do it on a measurement transformer. It can be done on a circuit breaker or a cable. It can also be done on any asset which has electrical insulation. The specifics of tan delta or power factor on rotary machines is that rotary machines tend to be quite big, physically large, especially generators. So because of that, the capacitance of such devices is bigger than the capacitance of, let's say, transformers or circuit breakers, etc., etc. And for that reason, sometimes tan delta and power factor are not absolutely the same. But as I was saying, that we have a big capacitance to combat, let's say, there is one more accessory which is necessary for tan delta measurement on rotary machines, and it's the reactor. So this is the reactor, the one to the right, while the first device is STS and TD, so our first choice to do a tan delta, or the TDX 5000, which is also a single function device made to execute tan delta and no load test on transformers. With these devices, we will often need to use, especially if we talk about bigger devices, the reactor. Let's see why. Before we answer that question, let us also repeat what are the elements of a rotating machine. We have a stator, we have a rotor, and we have the windings. So stator, rotor, and windings is what we have in a rotary machine, meaning that there is voltage phase to phase, there is phase to ground voltage, and there is turn to turn voltage. Also, there is phase to phase voltage, phase to phase insulation, phase to ground insulation, and turn to turn insulation. So these are the types of insulation, these are the types of voltages. Let's see how does that reflect onto what we have to do today. If we want to make an equivalent scheme of a rotary machine, it will be the same, for example, as the equivalent scheme for a transformer with primary, secondary, and tertiary winding. What we can see here on the right side of the slide is electrical scheme. It's the equivalent scheme of a rotary machines. We have two types of insulation. We have phase to ground insulation and we have phase to phase insulation. And let me remind you that when we talk about rotary machines, we are almost always talking about stator insulation. So phase A of the stator versus phase B of the stator, phase B of the stator versus phase C of the stator, phase A of the stator versus phase C of the stator. These are first three insulating systems. And then we have phase A ground, phase B ground, and phase C ground. These are phase A ground, phase B ground, phase C ground, and these capacitors represent the capacitance, the parasitic capacitance between the phases of our rotary machine. Now, there is one quite important thing when we talk about rotary machines, and it's the fact that if we have a motor, in some cases we will not have a chance, if it has a star connection, to disconnect all three phases. If that is not the possibility, then we effectively measure only one insulation. We measure the insulation between the stator and the ground. But if we can separate also the star point, then we can also measure insulation between phases. So I hope I made myself clear. If not, feel free to ask questions to my colleague, Mariela. We can see here some usual representations of a rotating machine. We can have it represented like this, or in general, as we saw before, like this. This is another way how to represent it, and here we're going to mention two norms: IEC 634-27-3, dielectric dissipation factor measurement on stator winding insulation of rotating electrical machines, and a newer IEC 60894 guide for test procedure for the measurement of lost tangent of coils and bars for machine windings. There are also IEEE 206-2000 tip-up tan delta test, which describes the tip-up and the tip-down tan delta test. Now, when we talk about, in general, tan delta, it's actually composed of three elements. So the tan delta is composed of conducting losses, polarization losses, and losses due to partial discharge. So conducting losses are the losses which happen because there is conduction. Polarization losses are losses which happen because due to the high voltage, the molecules of the insulating material inside become polarized and thus contributing to the electrical field inside our insulating material. And then we have losses due to partial discharge. Partial discharge, just to remind you, are sparks. And those sparks, micro sparks, better call them, also contribute to the overall conduction because electrons jump from one side to the other, and let's say they manage to escape this prison of not being able to escape the insulating material. So here we can see, again, we mentioned the tip-up test. So what is a tip-up test and why do we mention it? So we mention it because when we were, for example, talking before about the tan delta test on a standard transformer, we would not do a tip-up test. We would do a tan delta test on a certain voltage, 10 kilovolt, for example, and that would be it. Tip-up test is very often done with rotary machines, and it means that we start with 20% of nominal voltage as an excitation voltage, and then we go to 40%, then 60%, then 80%, then 100%. In some cases, if you want to overstress, you can go to 120%, but I don't think that is necessary. We do that in order to see how the tan delta changes with the increase of voltage. We do expect the change to happen, but that change needs to be within a certain margin, within a certain number. Okay, so coming back to the problem with the big capacitance and the reactor, how do we solve this? Well, before I tell you how do we solve this, let me just show you that if you wanted to measure a generator with 1 microfarad of capacitance at 8 kilovolt and 50 hertz signal, you would need to generate 2.5 amps. A simple calculation gives us that number. And in order to generate 2.5 amps at 8 kilovolt, we would need a 20 kilovolt amp output power from our device. This would mean that we would need to provide you with a heavy device, which is not the case. The devices we provide you with are between 20 and 30 kilos, and you can do a lot with them if you control them intelligently. And that's what we're doing here. We're doing that by taking a rabbit out of a magician's hat, or by using the resonance phenomena. So what does that mean? Well, long story short, it means this. If you have a big capacitance and you connect also some inductance in parallel to this capacitance, what you're going to create is that you're going to create a resonant circuit. This resonant circuit changes its impedance according to the frequency, as we know. At a certain frequency, this resonant circuit will have the highest possible impedance, which means effectively that it will take the least amount of current from our device. Having taken the least amount of current from our device means that we can make a smaller device and still give you enough current to do the measurement. So long story short, with the original device, you can generate up to 300 milliamps for 120 seconds with STS and TD or with TDX. If you have 2 RCTD units, you can generate up to 4 amps. These two will take the burden of, let's say, each one will take the burden out of 2 amps, and the generator of our TDX 5000 or TD 5000 will not be overburdened. So this is theory. This is how it looks in practice. As the frequency goes higher, at one point in time, the impedance will be the highest possible, at which point we will be able to generate the biggest possible, let's say the smallest possible current, and which will stress the generator of the device the least possible. So this is what is a given. This is the insulation, R and C, which we are looking for, and we are adding this L in order to be able to measure a huge capacitance. We don't need to do this trickery with transformers, with circuit breakers, etc. But since generators are big, we need to do it with generators. Even with motors, sometimes it's not necessary if they're not quite big. If they're big, yes. But when I say big, I mean more than a few mega. But with generators, almost always. So this is what it looks like. You're going to connect our test set to the motor or a generator, and then in parallel you will connect 1 or 2 or 3 or 4 coils. Each coil is 40 Henry, and with the combination of these 4 coils you can reach the best possible frequency, the frequency which is the closest to your nominal frequency in order to execute the test. This is another important thing to keep in mind. Now, when we do a 10 delta test on a generator, on a transformer, we always aim to use the nominal frequency, 1 or 2 hertz above or below. Here, you're allowed to go even up to 3 or 5 hertz, because sometimes it's not always possible to do it at exactly 50 or 51 or 52 or 60 or 61 or 62 hertz. It does change the result a little bit, ever so slightly, but don't go too far away, definitely not more than 7 or 8 hertz from your nominal frequency. This is the same scheme, but more detailed, exactly step by step, how it needs to be connected. This would be our generator, this would be our compensating reactor, this would be the connection to the compensating reactor, this would be the high voltage source and the control box of the TDX 5000. And this is how it would look like in a power plant. This is how it would look like in a power plant when everything is connected. The STS controls the TD 5000 that generates high voltage. 2 reactors compensate on the high capacitance of the generator. And these are phases A, B, and C, where we connected the generation and the measurement. Now, how do we practically execute this test? So what's the first step? The first step is put the ground of the motor or a generator's tank to the ground. So explicitly put it grounded. Just make sure you've done it. The second thing, if possible, disconnect the star connection or a star point. If not, then only one test will be executed. We will here continue this discussion under the presumption that you are able to disconnect. If not, then you will be just doing test number 7. The third step would be connect the test set to the motor and 4, execute the required tests. Now this looks pretty simple, but let's see what it looks like in practice. If we have a motor, so this blue stuff you see, that's a big motor, and we have connected the ground of the motor to the grounding of a workshop where we have been doing this test. So right now, the second, since we had a chance, we disconnected these 3 phases from each other, and we will be able to measure phase to phase and phase to ground insulation. We've done this, we took some photos, and then we decided to measure the capacitance and the 10 delta, meaning the insulation between phase R versus ground, phase S versus ground, and phase T versus ground. We also measured between phases R and S, S and T and R, and then we connected phases R, S, and T in the same potential, and we measured between the ground. So we did 7 tests. If you cannot disconnect, just show you, if you cannot remove this connection, then you will be just testing number 7. If you can, like we did here, you will be testing 1, 2, 3, 4, 5, 6, 7. And some might ask, why do I need 7 tests? Well, maybe you don't. Maybe you just need 1 test, and if you cannot open the starter point, you will be doing 1 test. But if you have a huge motor or a generator and you want to pinpoint the problem, then it's better to do 7 tests, because it will tell you exactly where you have the problem, on which phase, and whether you have it between the phase and the ground, or between 2 different phases. So for that reason, you want to do 7 tests. But as I said, if you are not interested to know where the fault lies, then you can simply do number 7 and that's it. How do you do the test? So first, we will generate on phase, let's say U, the first phase, phase R, and we will measure from phases S and T. How much do we generate? Now, it's not an easy question, but in general, I would say the values between 10 and 12 are completely enough. In some cases, more is requested, but the only question, why do you generate 10 or 12 or 15, is basically how to increase the polarization of your insulating material. This means that if you are doing the test at the nominal voltage, then nothing can, let's say, surprise you. But even if you're doing 0.7 or 0.8 times U naught, you are not making a huge mistake. Basically, you're not making any mistake in the measurement, because at the end of the day, what you're looking for is a big change in the value, not like 1/100th or 5/100ths or 1/10th of tan delta of percentage. It will be few tenths or maybe a whole percentage. So in this case, when we measure like this, we can measure what is the status of the insulation between phase 1 and the ground, what is the status of insulation between phase 1 and phase 2, and phase 1 and phase 3. Then in the next step, you simply do this. You exchange generation with measurement, and you will see in the next slide that it will look like this. We generate on phase 2 or phase S and measure from phases R and T. And by the way, I wanted to show you once again, these are the phases, and we connect to those phases in order to do the measurement. Now, of course, we will measure the status of phase 2 versus ground and phase 2 versus phases 3 and 1. And of course, you will understand that the third step will be generating on phase 3, measuring the status of insulation between phase 3 and the ground, and phase 3 and phase 2 and phase 3 and phase 1. You see that we repeat sometimes some measurements where you don't have to. I do it simply because it doesn't take too much of your time, and I always compare the results just to make sure that I got the same number. And then the seventh measurement, you need to put back again the short circuit here. You need to have a star, and then you do the measurement between the primary, let's say, and the secondary side. Let's call it like this, between the ground and the stator. How to interpret the results? Now you have some numbers, and you need to interpret these numbers. Now, it is not always easy to say exactly what are the limits, because it heavily depends on the type of insulation you're using in your rotary machines. As you can see here, if you have a modern epoxy resin or polyester impregnated insulation, then your tan delta shouldn't go over 0.5%. Now, that's a pretty low number, but these are modern insulation materials which can give you more insulating properties. But still, if they start to deteriorate, they have a tendency to deteriorate quite fast. On the other side, if you have asphaltic mica windings as an insulation, your tan delta can be between 3 and 5%. Having said that, these numbers are not written in stone, and of course, a much more important parameter would be the delta, would be the change in your last measurement results and your present results. Because if this change is very big, then you should investigate further. If the change is not very big, then maybe you can investigate next year or the year after that. So once again, let us repeat how to interpret the results. The first thing is to have an older result so that you can compare it to. And if you don't, then definitely you need to find out what type of insulation material are you using and what are the normal values for that type of material. Now, if you have a misfortunate situation where your capacitance decreases, and at the same time the tan delta increases, this is a situation where we can tell you that a general thermal deterioration is happening within your rotative machine. While if you have an increase in both parameters, you can be sure that you have some contamination in your windings, or you have some absorbed moisture, some water inside, which then are there and they make the PD happen. So I mentioned again PD. I want to try and explain here one thing, and that will be what's the difference between the tan delta and the PD. And let me explain it like this. PD are micro sparks which happen excuse me, here and now. and they might never happen, and everything might be okay, and then they can start happening one day, and in a very short period of time make a way, let's say dig a way for themselves and create a catastrophic event in the insulation of certain generator, for example. Tan delta on the other side is more of a statistical value of the status of the insulation of the whole electrical insulation. And how does it differ from PD? It differs because you see, with tan delta you get an idea, a number, how good is your insulation, but at the same time you could have some very few very critical points which are quite critical, but the rest of the insulation is fantastic. Overall you're okay, but sometimes these very risky points can start to deteriorate quite fast, and in that case the tan delta will increase and the PD will start to appear even more. So PD is right here, right now. You can also correlate PD with certain events of opening and closing circuit breakers, putting the generator on load, etc., etc. You couldn't do that with tan delta because the PD is telling you what is happening right here, right now, under these conditions. Okay, so having said that, let us continue and let's talk about a tip up and a tip down test. So as we mentioned before, with rotary machines, what we do is we don't just do, yes, we do just the value at one value of voltage, let's say 10 or 12 kilovolts, we do a tan delta, but then after that we measure tan delta. But after that, we do a voltage sweep. Voltage sweep has between, let's say, 5 and 7 steps. You can start with 20 and progressively increase to 40, 60, 80, 100 volt, 100 times U naught, and generate different voltages. Then you will go back 80, 60, 40, 20, and what you expect to see is that the tan delta and capacitance basically change as you go up in the same way as when you go down. That's what you want to see. If you don't have that, then you might have some smaller or bigger issues. We will see one of those examples very soon, but what I have here is one example when I was doing a tan delta test on a motor and I did not connect correctly. My ground of the motor and the ground of a test device was not connected to the same point, and look at the tan delta I got, minus 1,453%. Makes no sense. This is what you'll get if you don't ground correctly your tank, your test set, all of your test set, STS, TD, whatever. So just to tell you where to look if you are, so what to change if you get such crazy numbers. Then when I connected correctly, I got this number, 0.25. And that's a good number for a rotary machine. You can see that we did it at 1 kilovolt. The current coming out was 58 microamps, 50 hertz. Capacitance was 184 micro, 0.184 nanofarad. Now, moving on, let me explain when you actually execute a test and you get the results, how do you interpret these numbers? So what I was just telling you is that the tan delta, the value which we got 254 can also be calculated by taking into consideration the capacitance and the resistance, because this is what you will also get. The capacitance I measured is 184 nanofarad and 6,831 mega ohm. If you take these two numbers with this formula which you saw before, you will get the tan delta which we got here. Also, I want to explain one more thing, and that's why are we expressing the values of tan delta and power factor for that matter in percentages. Long story short, we just take the number and we multiply it by 100, and when we do that, we also need to add percents at the end, because the tan delta, the tangents of a small angle of, let's say, 0.1 or 0.5 degrees, it's an even smaller number. So instead of saying 0.005, you say 0.5%. That's to demystify that element. Now, what you can see here is another example, but this time we did a tip up test and a tip down test. This was done in South Africa. It was done uh, in a place which rewinds motors, so a motor shop. And what you might see here is that this is 6.6 kilovolt motor. So we have 20%, 40%, 60%, 80%, and 100% of nominal voltage, nominal volts. And then going back, we have 80, 60, 40, 20. So what you can see is we increased and then we decreased the voltage. Proportionally, the current increased up to 0.3 and then decreased. And actually, it was almost the same. You see 56, 56, 115, 115, 177, 177, 240, 240, 305. So this is exactly what you're looking for. The frequency wasn't 50, it was 57.7. And what is also good to see is that the capacitance didn't change. The capacitance shouldn't change at all. I mean, when I say at all, if it changes in the last digit, it's not a problem. But you see that the capacitance is 122 nanofarad, between 122 and 124 nanofarad all throughout. And that means that the measurement, okay, it's here 126, but this is due to the accuracy in measurement. Anyway, between 122 and 126 doesn't change much, which means that the measurement is stable, but tan delta changes. You see 0, 7, 1, 4, 2, 1, 2.6, 2.9, which is almost 3, which would maybe raise some eyebrows, but it didn't. And then we go back from almost 3 to 2.6 like it was here, 2.11 like it was here, 1.4 like it was here, and 0.77 like it was here. And that's it. And it's perfect basically because as you go up the same path you go down, and this is a proof that the measurement was good. And this was done on a motor where there was a star connection and we couldn't open this connection. So we just did a test between the stator and the ground. Okay. So let's recap. We should be able to perform tests as close as possible to the nominal frequencies. And also what we do automatically, sometimes we change by 2 or 3 hertz in order to remove the noise. And this is the example of yet another tip up and a tip down test, which wasn't that bad, but it wasn't perfect. So you can see that the tan delta for 1.4 here and 1.4 here is the same, but this is 107, 106, 132, 135, 139, 148. So there are some differences here, but still very close. So this shows you, in short, that it's not a perfect result, but it is what it is. And what will you continue to do is to keep an eye on this generator next time you do this test. To close the whole story, we're just 15 minutes from 3 o'clock. Let us shortly once again look to the comparison of tan delta and partial discharge. So just to recap, the PD are microsparks that partially bridge the insulation, while TD is more like overall statistical value of the insulation's conductivity. Tan delta shows us the overall state of the insulation, while PD is showing us if we have some issues happening right now, sparks flying right now, at this moment. 3. Seeing if something is happening right now, we can correlate certain events with the behavior of insulation. So if you see PD more when you open or close a circuit breaker, or when you change the position of on-load tap changer in your power transformer, or when there are any over voltages, then you will know, you will correlate these two information, and you will be able to draw some further conclusions from that. Now, continuous monitoring is the best solution for maintaining properly rotary machines. It is particularly indicated for very big generators. With this, I wanted to emphasize that today, most of the generators and big motors have sensors, which are essentially capacitive couplers, which are connected to acquisition units, which continuously measure partial discharge on those rotary machines. This is the best thing you can do for your device if for your rotary machine if you want to keep it long for a long period of time and healthy, because if you do this, it's like having a continuous measurement of all important functions on the human body. I'll compare it to that. And number 5, TD sees well the whole insulation, and the PD allows you to discriminate which part are the PDs generated from. We do a lot of webinars. One of them is PD on generators, and while listening to that webinar, if you would be listening to that webinar, you would see that there are between 7 or 8 very specific types of PDs between phases, between the phase and the ground. You have then inside the bubbles of a tape. You have it closer to the bar, further away from the bar, just in the middle between the top of the insulation and the bar. You have slot discharges. You have all types. So with a PD, you can also pretty accurately say where you have the problem. So long story short, it's now 2:46, and this was my last slide. I want to first thank you for your valuable attention. We hope you learned something new. And now let me see how many questions do we have in order to see if we can help Mariela answer some of them. In the meantime, I have to say that I'm very happy to see that there are so many people attending this. Mariela, feel free to join me if there are some questions you haven't had a chance to answer, so maybe we can read them.
Hi, Andrei. There are some interesting questions that we received during the webinar. Let me check which are the most interesting.
Please.
This one, for example, by Acute Potter. I have a question. What is the acceptance criteria for tan delta and tan delta and delta tan delta for an isolation subject to gamma radiation? And also for thermal radiation at 150 degrees.
Can you just tell me at what time did this question arrive?
17.
Okay, so I have a question. What is the acceptance criteria for tan delta and delta tan delta for an insulation subject to gamma radiation? That's a good question, to which I have to say I don't know how. I mean, gamma radiation for sure would make deterioration of electrical insulation properties even faster, but the numbers I have to say I don't have. Basically, what you would like to see is that between the 20% and 100% of nominal voltage, the tan delta shouldn't be more than 1%. So if you have 1% at 20%, you shouldn't have more than 2% at 100%. This is for a certain type of insulating material, not for all types. So I hope, but gamma radiation for sure would make it deteriorate faster, which in translation would mean that you would need to do this test maybe every, not year or 2 years, but every 6 months. So Mr. Podar, I hope that this answers your question.
You can go on in the list that are more or less all interesting.
Okay, can you tell me at what time is the next?
14:20.
20. Okay, if tan delta values are increased but capacitance values are same with comparison to the previous result, what may be the cause? In that case, you have a problem with the insulating properties, which means that the mechanics has stayed the same, but epsilon, the characteristic electrical, the ability of your electrical insulation to insulate electrically has decreased, because you got some molecules of water inside, because you got some other impurities, because you got maybe some voids. Your electrical insulating capabilities are decreasing. Okay.
14:27.
14:27. Is the acceptance criteria for the insulation subjected to environmental aging like radiation thermal defined in any standard? Well, as much as I know, no, but we can additionally check on that. And if we run into something which talks about radiation, as we saw before, we'll let you know. But gamma radiation, you can send us an email just to understand what are the quantities of this gamma radiation, because if they're very big, then probably you have even more experience than me how it affects the electrical insulation.
1430. 30.
Okay, Mr. Nuno Santos. If we can't open the star, can we detect a problem between phases? No, because there is no way to measure if all three phases are on the same potential. You would have to separate the potential in order to see which phase is leaking towards which phase or towards which ground. So that's a must.
There is an alternative solution that also you mentioned, Andrei, that is to perform the partial discharge measurement. And by that one, you can discover if there is problem between one phase and the other phase. And this method you can apply even if you can't open the start point of the generator.
Thank you, Mariela. Thanks for reminding me.
Then at 1434.
Okay, what is tan delta acceptable value for static and rotating machine? So for a rotating machine between 0.5 and between 3 and 5%, depending on the type of insulation, and for some others like transformers, let's say 1%, for circuit breakers even less. So it depends very much on what is the particular primary device we are talking about.
1436.
Is there any possibility capacitance is constant and tan delta has increased 4 to 5 times? Yes. I mean, 4 to 5 times, that's a lot. But if you were at 0.2 and now you're at 0.8, yes, that can happen if you have a bad quality insulation, which is very much attracting the water molecules inside, or if you have, for some reason, the layers which have unstuck from each other and allowing the air bubbles to be formed inside. So this is absolutely possible.
Then 1443.
Mr. Mehul is asking, why does tan delta value increase with increasing in applied voltage? It increases because the polarization of the molecules inside the insulating material, as you increase the voltage, the molecules polarize even more, and then they contribute to the conductivity. The point is that they polarize up until 12 kilovolts, and from that point on, they are all directed in the same direction. No additional voltage would polarize them more. Let me put it like this.
Then I kindly asked to Mr. El Sayed Abdel Majid if he could resend his question, because I couldn't understand exactly what he's looking for. Then 1446.
Okay, I think I might understand what procedure is to test 6.6 kilovolt motor. Basically, it's the same one we described here. So by the way, in the handout section, you will be able to see a PowerPoint, excuse me, a PDF of what have we been showing, and also when the webinar finishes, you will receive a separate mail with a link to the PDF and also to the recording of this webinar. So don't worry, you will not be left without any information. And if you're interested to see how our devices function, just go to www.altanova-group.com and search for TDX 5000 or STS and TD 5000 to do a tan delta test.
Now there are several questions that we received. The people wake up their curiosity in these last minutes. So okay. 1446, is it better to perform a tan delta test by varying frequency from lower to power frequency?
On rotary machines, we rarely do that. This is done more on bushings to check their inside, to check their insulation. In general, we don't do that on rotary machines.
Then
so
14.
Mr.
46.
Harold. Okay,
How frequent should I test the tan delta for hydroelectric generator 58 megawatt, 5 years in operation?
I think you should test it right now, and then depending on the result, if the result is good, repeat it once when you have every time when you have a yearly checkup. I would test tan delta every 1 to 2 years, for example, but everything depends on the number you receive right now. If the number is bad, then you might need to check every 3 months.
1447, through the test, if tan delta value changes, what is the probable reason?
The reason for this is that as the voltage increases, the water molecules and also the molecules of contamination, contaminants inside the electrical insulation get even more conductive. And because they get even more conductive, the tan delta increases. The tan delta is reversely proportional to the conductivity. The more this insulation is conductive, the tan delta is higher. Sorry, I'm sorry, it's not reversely proportional, it's directly proportional. So long story short, what does it do? It additionally polarizes the water molecules and the molecules of impurities in order to make it more conductive. That's why you see this.
Difference between tan delta and partial discharge.
Okay, we already replied to this. So in short, tan delta is a statistical value which describes the conductivity or the insulating properties of our electrical insulation, while the PD is telling us if there are some microsparks in our insulating system, so that we can correlate those maybe microsparks with certain activities, such as changing of the on-load tap changer position, switching on the circuit breaker, or switching off the circuit breaker, or some over voltages.
Are there other tests similar to tan delta?
Well, there are other tests which can tell you the status of the insulation. They are DC tests, but they're not like tan delta, because the tan delta is an AC test. I would say that it is the only test I know which has all these qualities, but there are other tests for insulation. For me, this is the best test for insulation.
Is the faster test for the isolation and more easy. The other ones are complementary, we can say. Each different tests discover different defects inside to the isolation.
Well, let's mention the DC test, which is done by generating high DC voltage onto the insulation, in which you are able also to understand whether you have a problem with the insulation. But in that test, for example, you can't measure better to understand where the problem actually lies. Is it phase A versus ground, or is it phase B versus phase C? So this is a DC test, which will tell you about the insulation, but the result will not be so repeatable, and also you will not be able to discern between different types of defects.
Then, is there any value in performing tan delta measurement at higher than the light frequency?
No, because it would change. Because you remember, the tan delta equals 1 divided with omega RC. Omega meaning the frequency. You would get a different number, and the tan delta values are given for nominal frequencies. So I would not do that. You don't have to do this in order to, let's say, cancel out the noise. The noise is canceled because of our technology. So there is no need to do this unless you want to play or make a, I don't know, a PhD with a special topic.
Taking in account also that in the standard, they mentioned that you can perform the test even at different frequency. The important that
just to emphasize,
you have enough signal to cover the noise. Another thing also that is not mentioned at which frequency. If you did the first test, for example, at 50 Hertz, to compare it to the results, you have to repeat the test at the same frequency. If you did at 25 Hertz, the second time you'll do the same test at 25 Hertz, so you can compare the results. We have to remember that the tan delta test, the results are comparative. It's not an absolute value.
Correct. Well, basically, it's a little bit of both. It's comparative and absolute value. And also keep in mind, let's say that you can do plus or minus 6, 7, 8 hertz, plus or minus nominal frequency, maybe 10 in some extreme situations, but not more than that. So if you have a 50 hertz as a nominal frequency, you will do it between 40 and 60, more or less. That will be it.
It's a main. So another question, how should I calibrate the TAN TDX 5000?
Sergey, you should send it to your distributor and then he will talk to our office. So that's the quickest and the best way to do this. Also, just to say that we have also a device which we call a calibrator, but it doesn't calibrate your TD5000. It is used as a reference value when you measure your capacitance and 5 or 4 values of tan delta in order to see if it's accurate.
Also, shall we remember that if Sergey is referring to the calibration to perform the test, that the TDX 5000 and all the other our equipment, before to take a measuring, check which is the field that is connected to the test set itself and perform the calibration of the bridge that we have inside to our equipment.
Correct.
So it's automatically a calibration before each test that we perform.
Yes. So thank you for reminding me, just to explain this part. When you press start, you should always look at the bottom left corner because it tells you what's happening. So the first thing you will see is load evaluation. We are evaluating how much is the load to understand how much power we need to put in the power supply to generate the necessary current. Then we have calibration, then we have measurement. And then once again, we have calibration and measurement because we always measure not at the nominal value, but few hertz above or half a hertz or 1 hertz or 2 hertz above and below the nominal frequency, just to avoid the noise.
So another question, what are the equipments used to measure a partial discharge at tan delta?
At what time is that question, Mariela?
1448.
We have 3 questions. What is the name
the
of the
first one?
Okay. What are the equipments used to measure PD and tan delta? Well, the equipments used to measure tan delta are STS 5000 plus TD 5000, where the STS serves as the brains and the TD 5000 as the high voltage generator and the measurement of the current, or TDX 5000 are for tan delta. And then for PD, we have Aquila, Micro Aquila, PD base 2, Alpha. We have different types of acquisition units depending. And then also, if you want to, depends on what type of asset are we talking about, then we will provide you with different types of sensors. So feel free to contact me later. You will see my email or to contact directly the distributor in your country if you have a need for something like this, because for tan delta, we have basically 2 types of devices. And for PD, we have many other types of devices.
Shall we remember that the presentation will be shared with all the people after the webinar, including the registration of this webinar. We will send a link by mail. Shall go on with the question? 1448
is this method used to determine PD in high voltage cables using tan delta? Yes, it is the same method. Once again, we can shorten this whole 1-hour presentation in 1 sentence when we describe tan delta. Tan delta is the measurement of current when I generate high voltage and understanding what is the phase shift between the current and the voltage. By understanding what is the phase shift, I understand what is the resistance, or should I say the impedance of that insulating material, and by measuring that very accurately, I can tell you at which state is it. It's the same for cables, generators, motors, transformers, everything. The only difference is that now, if we talk about cables, cables have capacitance even higher than the generators and motors, because that's how they are made. And if you want to test high voltage cables, then you either can test not very long portions of the cable, or you need the RSCTD if you want to test the resonating inductor if you want to test the longer cables. But long story short, yes, it's the same thing. It's absolutely the same thing.
Then 1449, let me to translate for you. Referring to have the generator clean and the atmosphere can affect the tan delta measurement.
Angel, if you can clarify a little bit, by clean, do you mean PD free or do you mean something else? Mariela, what do you think?
This one, if we have a transformer that have, for example, the bushing that are very, very dirty, we could start to have a part that conduct the electricity through the surface, and this
Yes.
one could influence our tan delta value. So
Okay.
always when we do a tan delta test, we have at least to try to have the transformer a little bit clean. I know I am a woman, I prefer to have a cleaned house. We are engineers, we should have transformers cleaned, not like an house, but quite so good to perform good measurement test. Then 1449, do you have the partial discharge test equipment for rotating machines?
Yes, we do. Yes, we do. We have, as I mentioned before, Aquila or Micro Aquila or PD Base 2 or some other acquisition unit. And for rotary machines, we will use capacitive couplers. There are different types of capacitive couplers depending on the voltage level, and more or less, yes, Mr. Limo, we do. And then at 250, can we do tan delta test for low voltage machines at 660 volts? Yes, yes, you can do them. The lower the voltage, the less important the insulation is. So of course you can measure it even with the very low voltages.
In the standard is not suggested, but you can do.
Correct. Which time must use tan delta, or any time for maintenance must do? If I understand Mr. El Sayed, it's good to use it, let's say, once a year or once every 2 years if we talk about rotary machines. Mr. Ali Baran,
yeah.
tan delta values are rising, and we want to understand whether the value is a local point or the entire winding. What should be the steps in this regard? You should try probably to do a PD test, because the PD test will tell you what type, if you have any PD, what type of PD do you have. That's what I would do, Mr. Ali Baran. Mr. Benjamin, would you ever expect tan delta measurements to decrease with an increase in voltage when testing individual bars or coils before winding? You could have something like this, but it would be due to the inaccuracies of measurement. It can change a little bit, but I did not see that with the increase of significant increase of voltage, the tan delta decreases.
Andrei, could also be because if you consider the partial discharge, when we reach the inception voltage, after that, the partial discharge going on to decrease. And this one brings the tan delta value below than value that you could find at a lower voltage.
Yes, you're right. You're right. But still, it's an indicator that you have voids inside of your electrical insulation, and that it doesn't mean that you have a good electrical insulation, but it's just that it's more difficult to find the fault in it. Okay.
1452.
For generators, use tan delta values are high. You said we also use reactor. For generators, use tan delta. If you have high tan delta values, then you have high tan delta values. The reactor will not reduce the tan delta values. Without the reactor, you might not be able to do the test because if you just have the TD 5000 without any reactor and you have a big generator, it will stop working and tell you that the burden is too high. So that's when you need to buy a reactor. Why reactor required for rotation machine like generators? Because generators are big and they have a high capacitance, and when you have high capacitance, it means you can store a lot of electrons, and if you can store a lot of electrons, you need a bigger device. Since we don't want to burden you with 50 kilo device, but with 20 kilo device, that's why we had to find the best possible way to enable this. Hello, I have two questions. What is an acceptable value of tan delta for global impregnation machineries? There is not one number, but we're always talking about values between 0.5 and 5%, depending on the type of your insulation and also the type of asset. The second question, to calculate tan delta between phase in case R on the high voltage channel, S on A channel, and T on B channel, is it possible to use the external inductance? If yes, how to connect to the instrument? RCTD, the reactor, is an external inductance, so it's basically you have to use it. If you have some other external inductance, then you can't connect it to our system. You need to use the RCTD, which is produced by ISA.
Take also in account that if you don't have a huge generator like we saw in the presentation, could be that you don't need the external reactance because the power of the equipment itself is enough. The main parameter to consider if we need the RCTD, the external inductance, to compensate the bigger capacitance of the generator is the capacitance of the generator itself. If you know this parameter, you can understand that you can use the test set standalone, or if you need the external compensating reactance.
Okay. The next question from Mr. Nunes Santos. Should we do the test changing the frequency of the test on the test set of a motor generator? Motor and generator always, they don't work, they're offline. So motor and generator are at a standstill, they're not generating or they're not rotating. What we do is we have to change the frequency on STS in order to get to the resonating frequency. We have a program which is automatically does that for you, and according to that number you connect 1, 2, 3 or 4 RCTDs, 1, 2, 3 or 4 coils. So the motor and generator are not working, but you are changing the frequency according to the load which the device measured initially. Mariela.
So let me translate you the question. The tan delta value can change if you are in a cold place or in a not place?
Yes, it can. Yes. Because the tan delta is also dependent on temperature, and we have a compensating factor which takes into account the temperature of the insulation. So yes, it can change.
1455th.
Can we measure tan delta bus bar of a generator and how to evaluate the result? I'm not sure. Can we measure
tan delta can be measured for all parts that we have always in everywhere, because it's a measuring of the isolation. We can measuring even the tan delta connecting to the bus bar of the generator. Like we saw in the previous slide, when we can't open the start point, we measuring the tan delta only by the bus bar by the terminal of the generator, so by the bus bar. Then 1456, let me translate. How much is the maximum voltage that I have to apply for the tan delta test?
We will say between 10 and 12, but you can also go up to your nominal voltage.
By the standard for the tip-up test, you should do the test from 0.2 up to 0.8, the phase to ground of the nominal voltage of your motor. Is this one what is maintained in the standard. This one,
Okay.
when you test all the winding, the interior winding. Then 1457 for you, Andrei.
So repeating the test at the same time for many times, it would affect the insulation or the performance of the insulation in the future. No, it would not. We probably will not do it 2,000 times, but if you do it 10 times or 20 or 50 times, you would have the same value. That's the beauty of the tan delta test, because it's very, 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 very repeatable. So feel free
Also
to
because
try.
we do an AC test. That is the normal way to work a generator or a motor. So it's not influence the insulation self.
Okay, so and then we have a few other requests, so you will receive the PDF. We are happy that you like the presentation. We thank you for thanking us, and we hope that we will be soon together. We have one last question. I see here, how good is using real-time PDMS in generators for condition monitoring? It's fantastic. So this is what we mentioned before, continuous online monitoring of PD on rotating machines is what is the best solution to extend the lifetime of your generator or a motor. It is not an expensive system. It's simply something which can extend your lifetime 20, 30, maybe even 40% and save you a lot of money. So if you're interested in something like that, we also do that, and feel free to contact me. I will now show you the last page. And since it's already 3:18, I will thank you for your attention. And once again, check your mails. In about half an hour or 1 hour, you should get emails with this link to the webinar which we had, and also the PDF of the presentation you just saw. So this is all from me. I would like to ask Mariela if she has something to add.
No, I know that people still have a lot of curiosity. I'm happy for that. You can be free to contact us, to write to our general mail or to the Andrei mail that was in charge for this webinar, as you can see in the interface that you have in front of you, in the monitor, andrei.sepcic@altanovagroup.com. And we hope that you like our presentation. Have a nice day to everybody, everywhere in the world. Bye.
Bye, everybody. Bye-bye.